Hello everyone, my name is Kevin Hicks and this is Lab 3, which is black hole in orbits. For my computational modeling project, I explored gravitational systems using VPython simulations. The goal was to understand how gravity influences orbital motion, first through a black hole model and then through a planet motion spaceship system. The black hole simulation helped me verify basic gravitational relationships, while the moon-planet spaceship simulation showed how small changes in velocity can completely change an orbit's behavior. The main physics behind both simulations comes from Newton's law of gravitation and Newton's second law. The gravitational force between two masses is given by the force of gravity equals the gravitational constant times mass 1 times mass 2 divided by r squared. That force causes acceleration, which we calculate using acceleration equals force divided by mass. And in VPython, the simulation updates position and velocity every time and every small time step using those relationships, basically integrating motion numerically. This lets us predict motion even when the forces are constantly changing, like in an orbit. In the planet-moon spaceship simulation, the system includes the planet, the moon, and the spaceship. The surroundings are the space around them, essentially anything outside their gravitational influence. For the initial conditions, the planet has a mass of 8 times 10 to the 27th kilograms and a radius of 4 times 10 to the 7th meters, which is fixed at the origin. The moon has a mass of 6 times 10 to the 25th kilograms, and the moon has a radius of 2 times 10 to the 7th meters, which is initially to the right of the planet. And the spaceship has a mass of 7 times 10 to the 12th kilograms, and it initially is next to the moon, which is to the right of the planet. So for the black hole simulation was my starting point and modeled a star orbiting a black hole using the same gravitational equations. By measuring the acceleration force, I could estimate the black hole's mass, confirming Newton's second law worked correctly in the simulation. It also visually showed how orbital speed increases as the radius decreases, a good check that my physics was right before moving to a multi-body system. And then on the right here, you can see my code and how the mass of the black hole is calculated using essentially the gravitational force. Then I moved on to the main simulation, the planet, moon, and spaceship system. Each object experiences gravitational forces from the others. For example, the planet pulls on the moon and both pull on the spaceship. In VPython, the net force is calculated at each time step, and then the velocity and position update. At the initial velocity, which is the velocity of the moon times 1.8, the spaceship first forms a big orbit around the planet, but when the moon comes close, its gravity pulls the ship off course and creates a really dynamic, chaotic path. It's a great example of how complex real-world orbital mechanics can be. This is a video demonstrating that. Essentially, the spaceship, which is this magenta, orbits around the planet, but when the moon comes in, it makes a really chaotic path. And it's not exactly a figure eight, which is which our goal was, but it's definitely something. And then possible errors. Like any model, there are a few sources of error. Numerical errors can build up over time because the simulation only approximates motion in small time steps. We also ignore things like air resistance, non-uniform gravity, and relativity. So this is still a simplified version of reality. And since the system is sensitive to starting velocity, even a small change can make the spaceship crash instead of orbit. And one interesting question I looked at was, what if the moon's mass increased? When I tried that, the spaceship was pulled more strongly toward the moon and often got trapped in its orbit instead of staying in the hypothetical figure eight. And this shows how unpredictable or chaotic three-body systems can be. It also reinforces that gravity isn't just about one dominant force. It's an interaction between all masses and it constantly changes. In conclusion, this project helped me see how we can use simple physics laws and computational modeling to simulate really complex systems. The black hole simulation confirmed basic gravitational relationships, and the planet-moon spaceship model revealed how sensitive orbital paths are to initial conditions. Overall, it deepened my understanding of gravitational physics, computational accuracy, and how even small changes can lead to totally different results.